Hi, I'm Steve Halladay, and this is our fourth video on bare metal programming for Raspberry Pi.
Okay, Steve, it's payback time.
As you may recall, in the first video we booted Linux just to make sure that our hardware worked all right. In the second video we wrote a very simple infinite loop program just to get our hands wet with bare metal programming. In the third video we reviewed computer architecture and specifically the Raspberry Pi architecture. In this video we're actually going to build the program that causes the LED on the Raspberry Pi to blink. This video will take a little bit longer because there's a lot of detail that we need to go into, and so I apologize in advance if it gets a little bit long. Before we get started, I want to introduce you to some publications, some resources that will be helpful to you. The first one on the list is the ARM Systems Developer's Guide. This is a full book that gives a reasonably gentle explanation of the ARM systems. You can buy this on Amazon. There's an ARM architectural reference manual referred to as the ARM. You can Google for this. This is very helpful as well. The ARM instruction set documentation. This is something that we'll use quite extensively in this exercise where we have to figure out exactly which instructions we can use. And the info center for ARM is also full of many documents that are very helpful. Finally, there's a Raspberry Pi peripherals document that you can find at this link. This document explains how the ARM interacts with the peripherals on the Raspberry Pi, which is, of course, very important for what we're going to do here. Before we get started, I'd like you to take a moment and think through maybe the pseudocode for how the blinking LED program would work. Maybe pause the video here and write it down. And when you've got it written down, then turn the video back on and I'll explain how I think the pseudocode works. The first step in the pseudocode is probably to turn on the LED. If we want it to blink, then we need to turn it on. Then we need to wait for a while and then turn it off again. And we need to wait for a while after we've turned it off so that we can see that it's been off for a while. And then finally, we go back to step one and we just sit in this loop. And this will give us the effect of a blinking LED. Let's start by considering the very first step, turning on the LED. Let's see if we can figure out how to do that, and then we'll move on to the rest of them. As you'll recall from our previous video on our discussion on the Raspberry Pi architecture, the Raspberry Pi architecture is a load and store architecture, which means that in order to operate on data, I have to load it into the registers, and then if I want to actually affect memory, I have to store that out into memory. Also, if I want to access peripherals, I use the same load and store mechanisms. It turns out that memory and peripherals share the same address space, so some addresses are memory and some are peripherals. You may recall from our original tour of the Raspberry Pi that in the corner of the Raspberry Pi card there is a set of pins that we referred to as GPIO pins. There is a peripheral that's a controller that controls those GPIO pins. We'll call it the GPIO controller. And the controller is, we access that the same way as we talked about the other peripherals. So if we want to talk to the controller, we would use a store command. And if we wanted to get input from the controller, we would use a load command. The controller also controls a few other things. For example, the green LED that is the ACT LED on the Raspberry Pi. So by writing certain data to the GPIO controller, we can cause the green LED to light and to blink. To simplify our life, the ARM processor actually has a store instruction which will allow us to take a value that's in a register and push it out to that GPIO controller. And so we'll look at how we encode that store instruction into machine language so that we can write something in GPIO controller. Before we investigate the store instruction, let's first look at how we encode instructions into machine language. I'm looking here at the ARM instruction set reference manual, and you may recall that in a previous video we created a simple infinite loop using a branch instruction. It turns out that the branch instruction is one of the easier instructions to encode, so let's look at that first. We can find that here in section 4.4. The branch instruction also serves as a branch and link. The branch and link part is if you want to do a subroutine and you want to be able to branch back to where you came from, but we won't be doing that in this section. You'll notice that the instruction is encoded into 32 bits. These high order bits here are the condition bits, and we'll talk about that in a second. And then you need to put a constant 101 binary in here. And then the L bit, which notice it says 0 if you want to branch and 1 if you want to branch and link. Since we're not using the link, we'll set this to 0. And then the offset is the number of instructions that you want to move from where you currently are, remembering, of course, that the program counter is going to be off by 2 because of the pipeline. So what we'll do is we'll encode each of these different pieces, and we'll come up with a binary number that we can then use in our hex editor. Section 4.2 of this same document describes the condition field, in other words, the high 4 bits that were in the branch instruction. In the branches that we've been doing so far, we've been branching always, which says that we're going to set those high 4 bits to 1110. If, for example, I wanted to branch based on some condition, if the Z bit in the current processor status register is set, then I would put in 0000 and so on and so forth for these different types of conditions. There are other instructions which affect the current processor status register, and they set these bits. So, for example, one instruction that might set a bit would be a compare instruction. And I could do a compare, and then I could branch based on how that comparison turned out, which of these CPSR bits get set. Back in the branch instruction now, we know that we want to set the condition to 1110. Okay. We know that we're going to leave these 3 bits as 101 plus the link bit, which is 0. And then the offset is going to be -2, which is FF, FF, FE. So altogether then this gives us a hex value of EA, FF, FF, FE. And as you recall, that's exactly what we encoded that instruction to be. So what we're going to try and do is figure out how to use the store instruction to control the GPIO pin. But before we do that, there's one other item we need to cover, and that's how to talk to the GPIO controller. I'm in the Raspberry Pi ARM peripherals documentation here, and we can look through this documentation in section 6. It talks about the GPIO controller, and you'll notice in this section here it talks about all these different registers. These are not registers in the processor, but these are registers in the GPIO controller, and you can see that there's a lot of them here. What we need to understand is that there are 3 kind of sections that we're interested in. The first section here configures the controller to be able to work with us, sort of like it turns the controller on. The second section here allows us to set values in the controller, and the third section here allows us to clear values in the controller. And these will be the only registers that we'll be working with at this point. You'll notice that these configuration registers, and in fact all the registers are contiguous in this address space, but the main ones start at this base location. This is called the base address for the controller, and then each of these different registers is relative to that base address. It says here that the base address is at 7E200000. In our address space, it'll actually be 2020. This has to do with the processor mode, and I'm not going to explain any of that at this point, but just know that where it says 7E20, we're going to use 2020. Okay? Now the first thing that we'll need to do is turn on the controller for the pin that we're interested in. It'll be pin 16, which this is not the pin in the corner of the Raspberry Pi card, but this is a different pin on the controller, and it's the pin that's hooked up to the green LED. And so the way we'll do that is we'll write to the register here at 20200004, and we'll write a specific value there that'll configure that to work with us. Then when we want to turn the pin on, we'll write to this register here, and when we want to turn the pin off, we'll write to this register down here. And this may seem a little bit confusing at this point, but hang in there and I'll show you exactly how this is going to work. Figure out how to encode the store instruction to affect the GPIO controller. Let's go back to the ARM instruction set manual. We notice here in section 4.9 there's a single data transfer. This is the load and the store instructions, and we're interested in that, so we'll take a look at that. Notice that this looks a lot like the branch instruction encoding mechanism that we used, only a little bit more complicated. So let's see if we can figure out how this ought to work. To encode the store instruction, we'll start with the same condition code like we had in the branch instruction. Once again, we'll want to store always, so we'll use the same always value, 1110. Now for these next 4 bits, the first 2 have to be a 01 on any load or store instruction. Then the I bit tells us whether this offset value that we're going to use here, whether this is a constant or whether it gets manipulated somehow. And we're just going to use that as a constant. So it says down here 0 equals offset is an immediate value, and that's what we want. So we'll put a 0 in here. Next we have the P bit. This has to do with pre or post indexing. We want to use pre-indexing, so we'll set that to 1. Now the next 4 bits start with the U bit, which has to do up or down. It means, is this offset added or subtracted from the base register? And you'll remember that from the base address that we have for our registers in the controller, we want to add a value. So we'll use the add, which is a 1. Okay. Now for the B bit, this tells us whether we're transferring a byte or a word. We want to use a word quantity, which is a 0 according to the documentation here. The W has to do with write back. Do we want to change the base address after we perform this operation? And we don't, so that's a 0 according to the documentation. And then finally, the L bit has to do with load or store. We're doing a store operation, so this is a 0 as well. These 2 fields are register numbers, and these register numbers contain the address where we want to store the data and then the actual data that we want to store. This register is called the base address register, and what we do to calculate the actual address where we want to store the data is we take the base address and we add in the value in the offset bits here, and that's where the data will go. And then this register contains the actual data. It doesn't really matter which registers we use for these. Any of the general purpose registers will work, but we'll just choose register 0 for the base address, which in the example that we're working with, this register will contain the value of 20200000 hex, which is the base address for the GPIO controller. And then this register will use register 1 to hold the data. And then finally, the offset, it could be, for the example that we're working on, it could be, depending on which register in the GPIO controller we want to write to, it could be a value of 4 or 1C or a value of 28 hex. So for this example, we'll choose the value of 4, so it'd be 00, 00, oh, let me put a space in there, make that a little easier to read, 04. So that's our 12 bits here. So now, if we take this entire value and we convert it into hex up here, I'll put it up here. Actually, I'll move it down here because it's a little bit easier to see the numbers. We end up with E5 80 1004. And so this is the instruction that we would encode, the machine instruction that we would use to encode this store operation that we want to use. Now we're ready to actually start building our machine language program. And here's the operation that we encoded, the store operation, and we encoded in machine language. So we'll start by putting that in. Actually, remember now, this may be a little bit confusing, but this is the low order byte back here. And so we want to enter that first. And then the next byte would be this one, and then the next byte is going to be this one, and the last byte is the E5. This is because on the hex editor, the low order byte is on this side, but in our decoding and encoding, we use it this way. So we just need to make sure we swap those when we get done. And then let's think about this after we actually do the operations that we need to for turning on the light and turning off the light. And by the way, I think it might be easiest for our first step to just turn on the light and then see if we can get that much running. Then the last thing we're going to want to do is sit in an infinite loop, and we learned how to do that from our previous exercise. And so that's going to look like this. It's going to be an FE, FF, FF, EA, right? And in fact, we can see that there's actually one more thing that we're going to need to do. We're going to need to do another store operation, but instead of storing a 4 like we decided down here, we know that we're going to have to turn on the LED, and so we're going to need to store this. Remember, this store instruction, it enables the GPIO controller. Then we need to actually write some data to it that will cause the bit to show up. In order to do that, we're going to write to address hex 28, the offset of hex 28 from the base address. So we can create that same instruction, 281080E5, and we see that this instruction here is just like this instruction, with the exception of the offset is changed a little bit here. So we're going to 28 hex instead of 4 hex, and we'll still be writing data from register 1, and we'll still be using base address 0. So now the question that we need to ask ourselves is, how do we put the base address value in the base register? So let's take a look at that next. Move a constant value into a register, we'll use a move instruction, and this is a data processing instruction. So we'll go to section 4.5 here, and we'll look at these data processing operations. We see that this operation, once again, this instruction starts with a condition code, just like we've used in the past. And so what we're going to want to do there is set that to always, like we have in the past. And we see that we have a 00 here. The I is an immediate operand. It's a bit that tells us which way we want to interpret operand 2 here. We'll talk about that in a second. Look at this here. This is the opcode within the data processing operation. And we can do any one of these operations. We can do an AND, an exclusive OR, a subtract, an add, and so on and so forth, depending on which 4 bits we set here. Finally, we have this S bit, which tells us if we want to set a condition code. If we set this to 1, this sets the condition codes in the current processor status register that we talked about. That's the Z bits and the overflow bits and all those kinds of things. And then we have some registers that we use as parameters for our operation, and then finally this second operand. Now the second operand is a little bit confusing. What we want to do is we want to use this version of the second operand. And the way you interpret this, the IMM is a single 8-bit value. And so you can store anything from 0 to 255 here if you wanted to. And then what you store here is the size of the rotation that you want to do on this 8-bit value. So for example, if I rotate with a 1 here, what it's going to do, what the instruction is going to do, is take that 1, it takes this rotate value, multiplies it by 2, and then rotates the right value by that many places. So for example, if my IMM had a value of 1 and my rotate had a value of 1, I would take the rotate, which is 1, multiply it by 2, so I would have 2, and then I'm going to rotate that 1 that's in the IMM by 2 positions. So it'd be 1, 2. So I'd end up with 0, 1, 0, 0, 0, 0, 0, 0. Okay? So it's a little bit confusing, but if you read through the documentation here, you can eventually figure that out. So now I think we're ready to encode this instruction. We'll use the same always condition code that we've used before, 1110. These 2 bits are 00, which says it's a data transfer instruction. The I bit here will need to be 1 because we want to use this interpretation of operand 2. So we put a 1 there. Our opcode needs to be the move instruction, which we find right here, 1101. So we'll put that in for our opcode. Yes, do we care about setting the condition codes? We don't want to change those, so we'll put a 0 in here. And now our register 1, we're not actually using this, so we'll just put a 0 in here. And then the destination register, this is where we want to store the constant that we're putting in here. So this we care about. We want to specify this as register 0. So we'll put register 0 in here. Now the final operand 2 is a bit tricky to encode. What we want to end up with ultimately for the value that we're storing into register 0, as you recall, is a 0x20200000. This is a 32-bit number. However, there's no way that we can directly move that value into our register with a single move instruction. What we have to do is we actually have to piece it together from a couple of move instructions. The first instruction will just move in the value 0x20000000, and then the next instruction will load in the value into another register 0x00200000, and then we'll AND these two registers together to get the final answer of 0x20200000. Now I know that's a lot to try and understand, but stick with me here and I think it'll start to make sense. So the first thing that we need to do is we need to load into register 0 a value of 0x20000000. Okay, and here's how we do that. We have to look at how this is encoded here. What this means is we take this rotation piece here, which is 4 bits, we multiply this value by 2, and then we use the result of that to rotate this IMM value that many places to the right. Okay, so if we want to end up with a 2 in the high order nibble of our 32-bit value, the way we would do that is we put a 2 in the rotate and a 2 in the IMM. And what that does is that rotates 4 positions, the 2 that's here. So it's going to rotate it 1, 2, 3, 4, and we're going to end up with a 2 in the high order nibble of our 32-bit value. So what that means is here we need to put in the value of 0010, 0000, 0010, and that will ultimately give us the value that we're looking for. So now we can encode this whole thing into a hex value, which will be E3, let's do this in capitals, E3 A0 02 02. Now we can enter that value that we've just encoded into our hex editor for our machine program. Remember, these are the low order bytes on this end, these are the high order bytes, so we need to reverse them when we put them in. 02 02 A0 E3. Now we're not quite ready yet. Remember, we still need to load in another value into a different register and OR them together. So let's go back and see how we do that. For this second move instruction, we'll want to load the value into register 1, so we'll keep all the rest of the bits the same, but here we'll put in register 1 for the destination register. Our operand 2 now, we need to end up with a little bit of a different value. We're looking from the previous value, we're looking at coming up with a result of 0x00200000. So what we can do is we can still start out with the same 2 in the immediate value that we had before, but this time we'll rotate it, instead of 2 positions, which was really 4, we're going to rotate it 6 positions, which is really 12. 6 times the 2 is the 12. So we'll take this 2, we'll rotate it 12 positions to end up where we want, and that ends up looking something like this. 0, 0, 1, 0. I'm sorry, I did that wrong. 0, 0, 0, 1, 1, 0. That's our 6. That's how much we're going to rotate. That times 2. And now we put the immediate value in, 0, 0, 0, 0, 0, 0, 1, 0. And that should give us the final result that we're looking for. So now we can encode this into hex like we did the others. We end up with E3, A0, 1, 6, and put a space in there, 1, 6, 0, 2. And now we're set with this instruction. We're ready to add that into our hex header. So here's the value that we encoded, and we'll put that as our next instruction in our hex header, remembering that we need to reverse the bits, or reverse the bytes rather, as we enter them in here. Okay, so now what we have is we move one value into register 0, and then we move another value into register 1. And then what we'll want to do is OR them together. Now, this is also, the OR operation is also a data transfer operation. And I'm not going to go through the encoding, I'll leave that up to you, but I'll show you what the result is. The result ends up being 0, 1, 0, 0, 8, 0, E1. Now at this point, these three instructions have put into register 0 the value of the hex value of 20200000. And now we need to do one more move instruction to get the data value into register 1 that we want to store. And the data value we want to store is a hex 00040000. This we can do in a single move instruction. And I won't go through the gory details of encoding it, but here's what it ends up being. 0117 A0, E3. Okay, so now at this point we do all this and we do the store instruction, and that actually turns on the GPIO controller for what we want to do at this point. Now, after we've done that, we need to add another move instruction to change the data address, and then we need to store the data in another location. Let me show you what those are going to look like. 0118 A0 E3. This is the next move instruction that moves the value of 0001 0000. This value is what we need to be able to turn the pin on. And now we're going to store that at address 40. And the way we do that is with a 281080 E5. Now all these instructions are instructions that you've seen at this point. I have one extra instruction here. Let's see. Here's the instruction. I copied it twice, didn't I? So this instruction goes away. Here we are. And okay, so now we're good to go. And so this is the program that will turn on the light right here. So you can save this one and you can run this one. This will turn the light on. So by this point, you should know how to turn the LED on, which we just demonstrated in machine code there. You can turn the LED off. We've talked about that. That's basically just writing to the other register that has a 28 offset from the base address. You know how to go back to step 1. This is like our infinite loop, but instead of going back -2, you'll go back however many instructions you have. So all that we really have left to talk about is how do you delay for a while. There are several ways to do this, but probably the simplest way, which we'll use for now, is just to go into a loop for 1,000,000 times or something like that. And that'll slow you down in between turning the LED on and off. How do you loop for 1,000,000 times? Well, you know how the branch instruction works. So the branch instruction works exactly the same way, except instead of branching always, the condition code will use a branch not equal. So for example, in your loop, you can have some register that's your counter register, and each time through the loop you'll add a value to that counter register, and then when you go to branch, you can branch if it's not equal to 1,000,000 or whatever constant you decide to use. That should be fairly straightforward. The only other instruction we haven't talked about is the compare instruction. The compare instruction is another data processing instruction, just like the move instruction we just looked at, and as well as the add instruction that you'll use in the loop to increment your counter. But with the compare instruction, the one thing that you'll want to do is you can use it to compare two registers, or you can use it to compare a register against a constant value. And so you can use it to compare against your constant value, something close to 1,000,000. But the one thing that varies a little bit with the compare instruction is here in the set condition codes. Here, you do want to set the condition codes in the CPSR register. So you'll want to have this S bit set to a 1. So when you compare your counter register to a constant value, if they're not equal, then the appropriate flags will be set, and then your branch on not equal, on the not equal condition when you branch, will allow you to stay in that loop until your counter is equal to operand 2 here. So now we've covered all of these instructions. All 6 of these instructions are everything we need to know to be able to actually create the blinking LED kernel.image file. I've prepared a kernel.image file here, and so all I need to do is open it in the hex header. Jamie, no, not the mouse. Oh, okay. So he cut the cable on my mouse. I can't open the file and show it to you. As you can see here, I tried to fix my mouse, but I wasn't very successful at it. I am a software guy after all. So I can't open the file and show you how it works, but what I can show you is the actual Raspberry Pi looping here. You can see the green LED blinking, shows us that it's working. I won't be able to actually show you the code, but at least you'll be able to figure it out based on the information I gave you, and part of the fun is actually trying to figure it out, so I'll leave you to that. We saw that this was very tedious doing machine language programming, so in the next video what we're going to do is build a little assembler to help us make life a little bit easier. Remember, if you have any questions, feel free to contact me at somepieguy@gmail.com, and I'll see if I can respond to your questions in future videos.